Here in this video, we're getting a continuation of our discussion of intermolecular forces and the impact that they have. So we've talked already about how they're going to influence phase, how they're going to govern something being a solid, liquid, or gas at a particular temperature, because those attractions can cause particles to stick together. Now we're going to move on and take a look at forming mixtures. In particular, we're going to talk about solutions. So when we talk about a solution, well, before we get to solutions, we need to talk about mixtures. We've got two types of mixtures. Mixtures can be homogeneous or heterogeneous. Now, homogeneous mixture, remember, is one that is the same throughout the entire mixture. So they are uniform. There's no visible boundaries between substances. So an example I tend to like to use is to think about a soda, because most people are going to be familiar with soda. Soda is a homogeneous mixture. If you open a bottle and you pour it into two different glasses, both are going to look the same, they're going to taste the same, because they're going to have the same composition of the mixture spread throughout that entire container of soda. So any homogeneous mixture is going to be that way. It's going to be the same throughout. The components are evenly dispersed throughout the mixture. Now, homogeneous mixture can be described one of two ways. It could be a solution or it could be a colloid, and sometimes we get these two mixed up. Solutions are going to have particles that have a diameter of 0.1 to 2 nanometers. They're going to tend to be transparent and they don't separate. Colloids are going to have particles with diameters of about 5 to 500 nanometers. They're going to tend to appear either milky or opaque, and they don't separate. So when we think about the difference between a solution and a colloid, look at the two of them. One of the first things that we see is a difference in particle size. So they're both homogeneous mixtures, but they consist of different particle sizes. So your solutions are smaller particles, your colloids are your larger particles. What they both have in common, in addition to having the particles spread throughout, is that they don't separate. So we've got solution with small particles, colloids with large particles. So there's one difference. They don't separate, which is what they have in common. And we see it said that one is transparent. The solutions are transparent, the colloids are not. So transparent being opaque has to do with light being able to pass through. So if something's transparent, light is passing through it. There's nothing blocking or preventing that light from moving through that substance. If something's opaque, that's because light is being blocked. If we think about the difference is because of the particle size. The larger particle size is going to block the light, causing the colloid to be opaque. So next we're asked, why is air considered a solution? So a solution is not just a liquid mixture that we encounter in a laboratory. We've got all kinds of different types of solutions, and air is considered a solution. So if you think about it, air is a mixture of gases. It's a homogeneous mixture of gases. We've got the same composition throughout that air. Thankfully, because otherwise, if we were in a room with people and one part of the room had oxygen and the other part didn't have that oxygen, people wouldn't be able to breathe. But instead, we've got the same composition of oxygen throughout that entire mixture of air. So air is a solution. Air is consisting of gases, which are small particles. Air is transparent. The gases don't separate. And again, they are homogeneous. And then next we're asked about milk. If milk is classified as a solution or a colloid. And that milk is going to be a colloid. It's going to consist of large protein particles dispersed amongst water. So we've got our large milk proteins dispersed amongst water, creating that uniform mixture, but we've got the large particles that are blocking the light, making that milk white or opaque. So just some generalizations of solutions. You guys should have encountered some of this information before, but remember that a solution is made of a solute and a solvent. The solute is the substance that we dissolve, and it's often the substance present in the lesser amount. The solvent dissolves the solute. It's often the substance present in the greater amount. Solutions or solutes and solvents can be in any phase. So we've got some examples of solutions here. We've got air. It's a mixture of gas and gas. So we've got oxygen, nitrogen, argon, and traces of other gases mixed together. Another example would be something like club soda. So that's going to be gas dissolved in a liquid. So carbon dioxide dissolved in water. Something like vodka or any other alcohol that someone might drink. It's a liquid dissolved in a liquid. So you've got alcohol, ethanol, which is a liquid dissolved in water. Seawater, we've got solid in liquid. So salts such as sodium chloride and magnesium chloride dissolved in water make up that seawater. And then we even have solid in solid solutions. So something like brass, in which we've got a mixture of copper and zinc dissolved in one another. So we can see a range of phases. Now, when a liquid is present, typically that liquid is going to be our solvent. Now, we're going to primarily deal with aqueous solutions in this course. They're the most common type of solution we encounter. These are the ones in which water is our solvent. And so again, we're going to primarily deal with aqueous solutions. Now, when we talk about solutions, we talk about solubility. So solubility is going to be the ability of a solute to dissolve in a particular solvent. That all depends on our intermolecular forces. And we're going to get into that in detail in our next video. But the ability of a solute to dissolve depends on intermolecular forces that are found within that solute, as well as what's in the solvent, as well as intermolecular forces that can allow them to interact. Solubility can also refer to the amount of solute. So it's the ability to dissolve, or it's the amount that is dissolved in a given amount of solvent. Again, that's going to depend on intermolecular forces, but it can also depend on temperature and pressure. Now, the formation of a solution requires that there is interaction between our solute and our solvent particles. And there are three important forces at work that govern solution formation. We have our solvent-solvent interaction. So before we even mix our materials, I've got my solvent. So say my solvent is water, and water is in that liquid phase. There are intermolecular forces that are holding the water particles together in that liquid phase. So when we talk about solvent-solvent attractions or interactions, that's the attraction that holds the solvent molecules together in their liquid or solid state. So if we're talking about water, it's what holds water molecules together in that liquid state. We also have solute-solute interactions. So again, we haven't mixed our substance yet. I've got my beaker of water sitting in one place, and I've got my container of solute sitting somewhere else. So say my solute is sugar. There are, again, intermolecular forces. They're going to be holding those sugar particles together in that solid state. And that would be my solute-solute interactions. Now, if I take my solute and I mix it with my solvent, those particles can also interact. So we can encounter solvent-solvent interactions. Those are going to be the attractions between the solute and the solvent. They are attractions that can break apart, or that can cause the solute to break apart and mix homogeneously with the solvent particles. Now, a solution will be able to form when the solute and the solvent can employ similar forces. So for them to mix, we've got a couple of things that have to occur. The solute-solvent interaction has to be strong enough to break the other attractions. So the attraction between my solute and my solvent has to be strong enough so that we can break the solute particles apart and we can break the solvent particles apart. That way they can get in and amongst each other and disperse. If we can't break those apart, then my solute can't move freely and it can't disperse uniformly. Now, often when we talk about solution formation, we talk about like dissolves like. You may have heard this before in terms of polar dissolving polar or nonpolar dissolving nonpolar. But really what we're talking about are the intermolecular forces. And like dissolving like all depends on the chemical nature of our compound. So we said previously, being able to distinguish your bond types in polar versus nonpolar is foundational for this course. Determining if a solution will dissolve, or a solute will dissolve, we need to know, is that solute ionic or molecular? Is it polar or nonpolar? Now, when we talk about like dissolving like, this is in referring to intermolecular forces. Like dissolving like means that a solute will dissolve in a solvent with similar strength intermolecular forces. Now, when we say polar dissolves polar or nonpolar dissolves nonpolar, that is because of those similar strength intermolecular forces. So, in our worksheet, we have a chart that we are asked to complete. Completing this chart will help us identify our bond types, polar versus nonpolar, as well as if we have, or what types of intermolecular forces we have. So, when we start with whatever our compound is. And we need to know if that compound is ionic or if it is molecular. So ionic versus molecular depends on the bond types. So ionic and molecular. Ionic compounds are going to have ionic bonds. Molecular compounds will have covalent bonds. So remember, with our ionic bonds are bonds between a metal and a nonmetal. So when we look at that formula, the minute we see that metal present, we can identify our substance as being ionic. If we don't see any metals, we see only nonmetals, then it is molecular. Now, if I have an ionic compound, that ionic compounds are held together by ionic bonds. Now, that's what's going to lead to that ionic compound being a solid. Those are not intermolecular forces. Those are chemical bonds forming that solid. Intermolecular forces would be that ionic compound interacting with something else. And so the ionic compound could have ion dipole interactions if mixed with a polar molecule. So ionic, we have to see if it's mixed with something to identify its intermolecular forces. Now, if we've identified our compound as being molecular, we have to further distinguish it as being either polar or nonpolar. So remember, nonpolar, you have either all nonpolar bonds or you have polar bonds with unsymmetrical geometry. A molecule will be polar if it has polar bonds. Oops, let's correct that. For nonpolar, we have symmetrical geometry, not unsymmetrical. polar bonds with unsymmetrical geometry give us our polar molecules. So each of these types have particular intermolecular forces available to them. If my compound is nonpolar, the only intermolecular force will be dispersion. If my molecule is polar, we have dispersion, we have dipole-dipole, and we have hydrogen bonding if we meet the criteria. So if I have hydrogen-oxygen, hydrogen-fluorine, hydrogen-nitrogen with lone pairs. So in this chapter, we've already talked earlier about using intermolecular forces in order to explain melting or boiling point differences or to predict who might have a higher melting or boiling point. And we went through this process. We just didn't draw it out in a chart. So we went through identifying, is my substance ionic or molecular? Is it polar or nonpolar? What types of forces do we have? Now what we're going to do in our next video is we're going to take a look at using these forces to explain solubility or to predict solubilities.